Good afternoon, everyone, and thank you for being here. I'm Michela Massi. I'm a first-year PhD student in Politecnico di Milano. Thanks to also the people that's behind me. I promise I will try to turn around a bit every now and then. So today I'm going to talk to you about a project that is actually pretty much work in progress, very much a work in progress. I will try to give you a bit of a background about the context that we're working on, and especially the complexities that we have to deal with. And I will try to do it by explaining one of the case studies, let's say the one I worked on the most. And actually, since it's a work in progress, I will try to go through the steps that we've been dealing with, also the mistakes or maybe the improvement that we did during the path, let's say. Okay, so the general context is that of cancer research, and in particular, prostate cancer. Prostate cancer is the most diffused cancer in the male population, and actually, luckily, is also one of those with the highest rate of survival. But since we treat patients with radiation, sometimes the radiation go and hit even the healthy tissue, so that the patients after a while might suffer from complications, from side effects, and some examples you can see on the slides there. They are not very nice things, therefore we are trying to find a way to tackle and to improve the treatment with radiation therapy even more. The problem is that the people that actually do experience these kind of problems are very, very little compared to the whole population, which is a very good thing, but it makes it very hard for statisticians to try and find them. This is why we're moving the attention towards genomics, and we're looking for the whole genome to find some correlations somewhere to understand how to address the treatments better. The data and the inspiration for this work come from a very, very big European project, which is called Requite. Requite is the biggest study of its kind that is collecting 5,000 patients affected with different kinds of cancers. And the data that we were provided with are in the form of SNPs, as S and P. If you're not familiar with the subject, I will try to explain it, even though I'm not a domain expert myself. So basically, as single nucleotide polymorphisms, or SNP, is a location in the human. Therefore, this is why we're looking exactly at SNP's location to understand the differences between population. So this is a very exciting field to work in, but it actually has some pretty intense complexities, and most of them, if you're working in the healthcare domain, you know very well. First of all, is class imbalance, exactly because of the reason that I just told you about. I mean, the people that is suffering side effects is very, very little compared to the whole group. We have a huge dimensionality of the problem, because like the SNPs within our genome are somewhere around 10 millions, and we have a small sample size. In our case, this is the biggest clinical collection of data that you would ever see, but it's actually pretty small if you compare it with the dimension of the data set. Therefore, still for statistician, it's really a hard thing to manage. Then, of course, we have noise that is both linked with the dimensionality, but also with the data collection and imputation procedure. So this is basically the context. Actually, we started with a smaller problem. So we decided to tackle one of the side effects, which is late urinary frequency variation after radiation therapy. Basically, you're having problem with your urinary frequency after 2 or 3 years you had radiation therapy. And the task here was not to look into the whole genome, but was actually to go back to previous studies, look at their results, and try to validate them. This is actually a pretty important problem in the field, because since the problem is so complex and the features you might look into are so many, every time that a study comes up with a new finding, the next paper goes with a new cohort of patients cannot find the same things. Therefore, if you really create a study that validates some of the previous findings, this is really valuable information for researchers and doctors in general. So this is where we started from. So we had a cohort of around 1,300 patients that had prostate cancer. 55 of them only experienced the problem with the urinary frequency. We looked into 43 SNPs in general, 9 of which were identified in previous studies. And let's say that the idea at the base of the whole our procedure is pretty simple. So basically what we're saying is, since the population that has the problem, let's call them unhealthy patients, since the unhealthy patients are so little compared to the whole population, we, instead of trying to build a super complex model to classify a super imbalanced data set, let's turn it, reframe it as if it were an outlier detection problem. So we have the healthy population, that is the general population and the normality, let's say, and then we have a few observations which are anomalous and can be considered the outliers. In the process of trying to identify those outliers, we might actually have some important information on what makes these outliers outliers. So to do that, we exploited a deep sparse autoencoder, which you probably know is a neural network that has the task of taking an input, mapping it into a latent representation, and then trying to reconstruct back the input as precisely as possible. So basically, we trained our own autoencoder just on the healthy patients because we wanted it to learn how healthy people is made, to say it in bad terms, I say. And then we tested it on both healthy and unhealthy patients under the hypothesis that once the model sees something that is pretty anomalous, it should commit a bigger reconstruction error. So first of all, just a little note, why we are using deep learning is not just because it's super fancy, but actually there are some pretty solid reasons, and the main intuition is behind the so-called central dogma of biology that states that the genotype decides the phenotype by following a hierarchical path, which means that, for instance, from DNA to RNA and so on. And actually, deep learning is basically born to mimic this kind of hierarchical processes, together with the non-linearity that we actually find in genome, because most of the traditional methods are, in statistics especially, start from the assumption that all the features are IID, which is pretty unreal when we talk about genome. And we realize that deep learning maybe has the potential to tackle and to learn a little bit more about the non-linear patterns of interaction that we might have within our genome. So this is why we're using a deep autoencoder. And this is why we are using it to try and learn how healthy patients are made, but we still have pretty few observations. So to tackle that, we basically we put the model into a bigger process. So we start from the cohort. In the cohort, we have a lot of healthy patients and just a few unhealthy patients. We start by sampling. So we take all the unhealthy patients and we put them directly into the test set. And then we sample from the healthy ones the same number, and we put it also in the test set. All the observation, all the healthy patients that we didn't sample, we put them in the training set. So we train the model, and then we test the model on the test set on both healthy and unhealthy patients, and we collect the reconstruction error. Then we go back again to the cohort, and we repeat the same process for a sufficiently large number of times. Once we have done that, we come up with a big matrix of reconstruction errors that has the patients on the rows and every feature, meaning every genetic location on the columns. We can split it because we have the information on who is healthy and who is not, and we can compute for each feature, meaning for each genetic piece, the mean reconstruction error per group. This is the result of the case study I was mentioning before. You would come up with something like this. So basically, we have all the SNPs on the x-axis, and we have the reconstruction error on the y. What we would expect to see is for the reconstruction error on or at least on some of the SNPs, to be bigger for the unhealthy population. Our first approach to this was actually pretty naive, so we just decided to say, okay, let's pick all the features that had a higher average reconstruction error. So basically, this is what we resulted with. The yellow ones that you see there are those that are mentioned in literature, so we are picking quite a few of them. But of course, the first thing that all of you are thinking is, yes, okay, you're picking them, but you're picking up a lot of other things, so this is not really valuable. This is why we actually moved on from this approach. And we wanted the difference between the healthy and unhealthy population to be really significant. In order to do that, we have plenty of different possible approaches that we didn't even have the time to try. But the fact that we have this big matrix that actually produces a sort of distribution of reconstruction error for each of the features allows us to do plenty of different things. The approach that I will present now is basically taking the distribution of the gaps between the two columns that you saw before and put a threshold on the differences, meaning that we are just taking care of the features that are actually pretty much different compared to the healthy population. So we started by proving the concept on a very famous data set that, of course, you know, but especially because it is pretty easy to see what is going on and understanding whether it makes sense according to our hypothesis. So basically, we started from the NIST dataset. We created a new dataset. We created a dataset from there where the digit 1 was the majority class and the digit 7 was the minority. We did the whole process. So the images that you see there on the top left corner, you will see the average reconstruction error on the minority class, while on the right you will see the majority class. Of course, the error on the majority class is lower because the autoencoder is learning just to reproduce the majority class. On the bottom part, you will see the delta reconstruction error, which is the difference between the minority and the majority. And then we put the threshold, which in this case is 0.95. And the features that you see there are actually the features that are supposed to be the most relevant in order to discriminate between minority and majority class. And actually, if we look at the average 7 and the average 1 that we had in our data set, and we superimpose the features that we have selected, you can clearly see that the features that we select are those where 1s do not exist, or those where 7 do not exist. So basically, they really are the places in the pixels where most of the difference between the two digits is lying in our data. Then we wanted even to test whether these features that we're selecting are helping us in trying to classify the minority class. So basically, we took a new data set from the beginning. We set it aside. And we trained and tested 4 different classifiers using only the features that we selected against all the features that we did not select. Of course, the NIST dataset is a pretty easy problem, so we're not surprised that the values are super high in any case. But an interesting thing to note is that by using a smaller number of features, we're still obtaining at least the same performance than by using all the features, which is already a good thing if you just want to do it as a feature selection process. And the other interesting thing is that actually moving the threshold higher, so from 0.85 to 0.19, and reducing the number of variables, if you look at the performance of the logistic regression on the minority class, it is actually improving, which is another pretty interesting result. So we did this on the data of the previously mentioned case study, and what you see there at the top is the difference between the columns, and then the delta distribution that I was talking about. The four lines that you see, the vertical lines, are the 4 thresholds that we tried, because of course there's no rule on where to put the threshold, so we wanted to test the robustness of the system. And those are the last results I will share with you today. So basically, those are the 4 thresholds I talked to you about. In the table, you find the SNPs that were previously mentioned in literature. As you see, right from the first threshold that we posed, which is 0.75, which is not very high, it's just the right side of the box plot, the easiest box plot you would come up with. Basically, the number and the SNPs that we find are always the same except for the highest threshold. Another interesting thing to notice is that the total SNPs that we're selecting, so the features that we deem relevant, are much lower compared to the previous attempt. And the last interesting thing to notice comes when we went back to the papers that were talking about these features. And what we noticed is that the 4 SNPs that we identified were those that had the highest odds ratio in their studies, meaning on other people, other population. This means that probably those are the features that are, in that case, were the most correlated to the outcome, and apparently in ours as well. So this is another interesting result that maybe suggests that we are going somehow in the right direction. There is no concluding slide, no conclusion slide, because of course there's no conclusion so far, but there are so many things that we will try to do and we way to do. So here is just a list of ideas, for instance, trying to tackle it through multivariate outcome, because as I told you, there are many different side effects, and it would be super interesting to understand how to model them at the same time. And of course, move it from testing on 43 SNPs to like scaling to the 6 million and trying to find a way to really do science on such a huge number. So that was it for today. Thank you for listening, and if you have questions, I'm here. Okay, yeah. Okay, thank you for the question. So actually, the point with it is that like every time, basically it's a non-supervised context. Every time that you find something, it might be right, but it might be wrong. There's no real answer there. So the SNPs that we had in our data set actually were found as correlated to some other similar side effects. I mean, we were still talking about the same subject, so late toxicity in any case. But we couldn't find any proof of the fact that maybe the 2 additional features that we found were actually correlated. There's no study about it, so we cannot really tell. But it's too bad. I hope someone will look into it at some point. No worries. Thank you.
Yeah, thanks for the presentation. What I did not yet get is, what is the input form of your data?
Oh, okay. Okay, yes, thank you. Like, I will show you. I didn't mention it, but it actually was there. So basically, there's an encoding for the SNPs, which can be 0, 1, or 2. 0 means that in that location you don't have mutation. 1 means that it's homozygous. 2 means that it's heterozygous. Actually, it's even more complicated than that, because like since the genome is made of 10 million SNPs, you cannot really go to the lab and measure each of them and be sure so that you put 0, 1, or 2. So what they do actually is to measure precisely some location that they know are important, and then they interpolate. So when we opened the data, actually, we were expecting 0, 1, 2. No, it was a continuous value from 0 to 2, which adds a lot of noise, because where do you really round? So,
do you have a timing structure?
Do you have?
Is there a timing structure?
A timing structure?
Like if I take a look at this thing, it looks to some extent like a time series, so it has a meaning that the A is equal to.
Ah, okay, you mean the position?
Yeah.
No. I mean, not in general. Like in your genome, it does have a meaning, not in the data. They told us that there was no reason, because actually you split the measurement and the imputation into different centers located around the world, so basically it's random. No way.
You say you have some constraints with the number of patients that you're using, but you say that the data set is for like 15,000 patients?
No, 1,500.
For genomic data, how much? I mean, I think 1,000 patients, I mean, for my experiments will be enough, but I don't know in genomics how much patient you actually will need to be just like representative of what you want.
Thank you for the question, but the problem is that, like, for me, coming from statistics, I would start from how many features do I have, and try and think from 10 million what makes an N sufficiently large. It doesn't exist, basically. So we just have to go with what we have and find a way to extract as much information as possible from the observation that we have. Like, yes, we haven't really tried it yet. The problem with that is that since there's so much noise and we are not even sure that the data is clean enough, you wouldn't go and try and create new data that starts from a wrong basis. I don't know how to say it. Like generate new data on fake structure. That would be very bad.
All right, thank you very much for this great work. I think it's really interesting how we can use the deep learning and autoencoders not only through images, but also to this radiogenomics and other stuff. Thanks a lot. And now we're switching to the next speaker.